forward, and now has moved his way into machine learning. So he's the head of data science, and he'll tell us what's happening at the MeerKAT project and also SKA, because they are kind of combining into the same thing eventually. Maybe I'm a little out of the loop on that one. But cool. So thank you, Bruce. And he also let me know, like, if you have any questions or anything, you can pop it into the chat or just break in. That's perfectly fine. And you can just give a wave or something on the chat, and we'll let you talk. All right, cool. So take it away, Bruce.
Awesome, thanks. So, yeah, please do interrupt. It's much more interesting, and I mean, I've taken a guess as to what I think will interest everyone, but of course, I didn't know who was joining, so it'll be a specific take. And if you've got questions, yeah, very happy to have the conversation go in a different direction. So please do just jump in. Just a question, can you see the video up here? I'm not exactly sure because it's covering part of my... Okay, so the top part is covered, is it? Okay, cool. So this is work. So I've been at SKA now for probably about 3 years, and so I'm going to just present a bunch of work with the team: Richard Armstrong, Christopher Finley, Michelle Lochner, Nadeem Mazir, Ethan Roberts, Alireza Varfae, and some other people. So a lot of it is not my work. So it was really nice preparing this talk because I realized okay, cool. I realized that, I haven't given one of these kind of, I've been so focused on data science and machine learning for the last 5 years. It's actually been, okay, good. My video was frozen, so just shout if it freezes and you lose audio. It's been a while since I gave an astronomy talk, and so just a brief reminder about what cosmology is. In a sense, it's, of course, the study of the whole universe, and SKA is one of the most exciting telescopes to address it. I love this definition, in a sense, by Georges Lemaitre. He was actually a Catholic, a Jesuit priest who studied cosmology. He was one of the first people to suggest that the universe was actually expanding, and he said, "The evolution of the cosmos can be compared to a display of fireworks that has just ended. With some few red wisps, ashes and smoke, standing on a cooled cinder, we see the slow fading of the suns, and we try to recall the vanishing brilliance of the origin of the worlds." Such a beautiful poetic description. So I'm gonna come at it as, like, how do we address this kind of poetic question using data science? And so the note, of course, in business value is very important, and it's no less true in science. It's just that business value is very different. Can I just check that I'm still online, because my video has frozen? Tuso, can you?
Everything's fine. Your video in the corner is not working, but the video below is working perfectly.
Oh, okay, awesome.
So no worries. We'll let you know if there's any hiccups or anything.
Great, yeah. I saw a funny cartoon that said that 2020 is basically like holding a seance. Like, Joan, can you hear me? Do something if you can hear me. So actually this image is a representation of a movie. I don't know if anyone can guess. Those of you who are friends of mine on Facebook, you will have seen this. But this is actually the average frame. So this is the average over about 200,000 frames from a very popular movie. And so this is simply a mean. Every pixel is the mean over the corresponding pixel. Any guesses to what movie it is?
Is that Interstellar?
Good attempt, but it's not. I won't. It's pretty random. I would never have guessed. It's the seventh Star Wars. But what you can see are these white dots, which are very interesting. And at first, I was very surprised. But the best suggestion of what they are, because I asked people on Facebook, is that it probably is that they use the same star field for many, many shots. And so what you've seen is that when you average over all of them, you see the stars come out. And that's actually very similar to what we do in many places in astronomy and cosmology. We're looking for very, very faint objects. And the noise is often as big or bigger than the sources. So we take many images and then we stack them together. The noise cancels out on average. Some of it's positive, some of it's negative, but the signal stacks up. And so this is quite a nice model for.
Oh no, I think we lost Bruce for a second. I'll put on some random head movement until he comes back.
All right.
Awesome. short.
Try that again, shall we? So I don't know how long. Where did you lose me, or where did I lose you, rather? Let's just maybe try to. Maybe I'll just try and share a single tab. That might have an advantage.
Yeah, I think you're still here.
Okay, perfect. Yeah. So I will move swiftly along. So I think one of the key things about data science is obviously the science of in the title, and one way, especially when you're interested in cosmology or fundamental science, I think it's very important to distinguish between the universe and the models that we build of the universe. And so the way I quite like to describe it is, we have this apple, which is the some aspect of reality. The scientific method obviously allows us to carve it up into smaller and smaller pieces. And then, of course, what we do is we try to reassemble it into some representation of reality. And at least in theoretical physics, it's often it's tempting to forget that our models are just that. They're not the universe itself. One of the reasons why it's easy to forget that is that, the span of physics and cosmology is so vast. It goes from, 10 to the minus 12 meters or smaller, all the way up through, the planets, through stars, here's the sun, through giants. Here on this scale, I love this picture because on this scale, the sun is 1 pixel. So Antares, a red giant, is massive. But then, of course, we go up to galaxies. So a galaxy would typically have 100 billion stars in it. And then we get to clusters of galaxies. So each orange object here is itself a galaxy with 100 billion stars, typically. And then if we zoom across, and so yes, with these galaxy clusters, light would typically take a million years to cross it. And then we can keep going. This is a survey called the 6DF. So each dot here is a galaxy, and we can look at the structure in which galaxies themselves cluster and form voids, almost like soap-like bubbles. And, the true extent of the universe is that it's billions of light years across. So when we look at the most distant objects in the universe, it's taken billions of years for that light to reach us. And of course, we're not just interested in mapping the universe, we're interested in understanding. So this is an image of my keyboard that I made to try to illustrate our current understanding of the budget of the universe. So a few percent, just a very small percentage of the universe is made up of ordinary matter, mostly hydrogen and a little bit of helium, and then very, very trace elements, almost like seasoning, salt and pepper for all the other molecules and atoms in the universe. The rest is made up of either dark matter or dark energy. So dark matter is invisible, but it clusters under gravity the way we know it does, and the way normal stuff clusters, the way that if you fall off a ladder, gravity shows you which way is down. And then, in fact, we think about 70% of the universe is made up of dark energy, which doesn't cluster under gravity. It's effectively anti-gravity, and it's causing the universe to accelerate. So the universe is expanding, but we found out about 20 odd years ago that the universe is not only expanding, but it's actually speeding up. So it's accelerating. And we really don't understand what that stuff is. And so, when we talk about business value for an astronomer or cosmologist, or they would never use that phrase, is about how do we learn about the universe? How do we understand these keys in a way that leads to enhanced understanding of the universe? So MeerKAT is a major South African contributions to this. It's actually certainly one of the 1 or 2 or 3 most sensitive radio telescopes in the world. It's made up of 64 dishes, 13 odd meter dishes. And just a point about these dishes, having multiple dishes is very, very powerful, because what you end up with is effectively a telescope with the same angular resolution as a single telescope that covers the same area as this collection of telescopes. And you can see that this was one of the first images taken by MeerKAT, or in fact probably by KAT, when there were only 7 dishes. Then an image of the same region when there were, I can't remember, but say 15. And then over here when there were 32, and then finally with the full 64 is probably over here. So as you add more and more dishes, you get deeper images, but you also get more and more finer resolution. And so this culminated, I guess this was one of the first really beautiful images to come out of MeerKAT. This is the Milky Way, the center of the Milky Way. You can just see these amazing shock waves, supernova remnants. This is a star that exploded and pushed out the shell of gas. Amazing image. But this is, of course, all building up towards the SKA. So the SKA will have 2 phases, we hope. The first phase is about a 10% 10% of the final square kilometer area, and we'll have a budget of about 650 million euros, and that is what we are transitioning into. MeerKAT will transition into SKA phase 1 along with Australia. And so instead of 64 dishes, I don't know the current numbers, but I think there's 200 odd dishes in the Karoo. And the full phase 2 array will have a data rate of about an exabyte a day. So that's quite a lot of data. Currently, MeerKAT has about 20 odd petabytes of storage, but an exabyte will be, is clearly a big step up.
We got a question quickly, Bruce.
Yeah.
Someone asked, why use orange for illustration? Why not color maps or similar kind of color schemes with those images you showed?
Why just use this? Yeah, I don't know. I wasn't involved in making those maps. So good question. You certainly could recolor them. There's nothing fundamental about about that choice.
Yeah, they always made it sound a little bit spacey, so you can tell it's in space because it's red, but space is red.
Absolutely. Yep. Any questions, just shout. So there's a few challenges that we are looking at, or at least that I think are kind of interesting from a data science point of view. The first, of course, is just this data wrangling. The second is RFI, source detection. I'll describe each of these. Then the Internet of Telescope Things, scheduling, discovering anomalies, and then we can talk about other things like the quest to be sensitive and unbiased. And of course, it used to be that we would say, it doesn't matter if you're a bit biased in machine learning. It doesn't matter. But I would, I've given variations of this talk for 5 or 6 years, and I'd often say, it doesn't matter so much if you are a bit biased in machine learning. But in science, it's absolutely critical that you deal with your biases. And of course, in the last, I guess, 18 months, that has completely changed. In machine learning, now bias is a real issue. So there is perhaps interesting work that can be transported from science to industry. And then maybe if we have some time, we'll discuss artificial intelligence as scientists. So of course, the first challenge is pure data wrangling. And I mean, as we all know, that cleaning data, prepping data, getting the data pipelines right is a huge part of any data science job. Just to put it in perspective, the SKA is looking at about an exabyte of data a day, and that's roughly 10% of all the information produced by humanity prior to the year 2000. I mean, it depends exactly what you mean by information, but the mere fact that in one day you can get within a stone's throw of what humanity produced prior to the year 2000 kind of illustrates the extent of the problem. MeerKAT currently, we have about, I guess, 10 terabytes a night, but that is with massive downsampling. So, for example, we take data at somewhere around, let's say, 50 microsecond time resolution. And we immediately downsample to 2 or 4 or 8 seconds. So immediately we'd reduce the data by, well, nearly 1 million, but let's say certainly 10,000. So we say it's 10 terabytes, but if we were to try to store the current data streaming off, it would be 10 terabytes times by 10,000, So it would already be, MeerKAT would already produce a lot of data. So we're already having to throw away data simply because we can't wrangle it or save it. But let's get into some of the actual kind of algorithm science problems. The first really interesting one that's very important is radio frequency interference. So, the analogy I give is, imagine you're at a very noisy cocktail party. You're in a noisy cocktail party and you're trying to eavesdrop on a conversation in another country. I mean, clearly it's insane, right? Humans couldn't possibly do that. But that's exactly what we're trying to do in radio astronomy, because MeerKAT is sufficiently sensitive to be able to pick up a cell phone signal around a neighboring star, Alpha Centauri, for example. And yet, on Earth, almost everybody has a cell phone. And so there's this really loud chatter, and we're trying to detect effectively the signal from a single cell phone around the neighboring star. So that's the kind of challenge, the order of magnitude of the challenge. And so here's an example from actual MeerKAT data that Nadeem gave to me. So the data we typically look at will look like this. It'll have frequency of the radio waves on the one axis, and on the other axis there'll be time. And you can see that there's all this stuff, these bits that stand out. I hope you can see my mouse. All this stuff is radio frequency interference. It could be from satellites, it could be from GSM, from cell phones, it could be from airplanes, aircraft, it could be television, radio, whatever. There's a lot of sources of radio interference that you would have to try to remove in order to see the signals you actually care about. And then there's also really weird stuff like this stuff, which maybe we've never seen before, and which we don't actually know what's causing it. So that's, both of those are there as sources of interference. So what's the solution? Well, the obvious one is to say we'll use machine learning, right? Let's train an algorithm to detect RFI based on some existing samples. The problem is we have no data, training data for specific RFI. So the training data is imperfect, because we can go and ask humans to draw a line around the RFI, a bounding box, right? We can say, okay, draw a bounding box where you think the RFI is, and every astronomer will do it in a different way. So in other words, we end up with contaminated training data or noisy training data. And of course, this is not unique to astronomy. Any kind of machine learning where you need humans to label your data and the labeling is subtle will have this kind of problem. But since we're trying to detect such faint signals, this is a real issue. So what's the solution? One solution, which is the one that we've taken, is to build a simulator. So we simulate RFI, so then we know exactly what is RFI and what's not RFI. So, just to go back, the use of human data for training in science is really, really problematic. I mean, it's problematic in the real world as well, but there, typically the margin for error is a bit bigger. But this is one of my favorite examples of the dangers of human labeling, which I think we all know very well. So this is the probability of parole from the Israeli High Court justice system. So this is the average of the probability of parole over, I can't remember the details, but it's over, say, I've ordered 10 judges, all of whom had a lot of experience. And so the question is, well, you see that the probability of parole goes from nearly 80% down to 0%. And so, whatever is on the x-axis is clearly critical in determining the probability of parole for a prisoner. And so you might ask, well, what is it on the x, what is the x-axis? And for those of you who've may have come across this, you can maybe think about what it is. The key is to look at these dotted lines. What could be these dotted lines? It turns out that the x-axis is time of day, basically. And so if you are seen by the judge, first thing, your chance of getting parole is very high. It just basically monotonically decreases until basically it's zero. If you're the last person before lunch, you're literally holding up the judge from their meal. They're not going to forgive you for that clearly bad timing. It's like that joke about someone said, I always, when someone who was hiring for a job, they just take half of the applications and throw them in the dustbin, and they say, we don't want to hire unlucky people. So if you're the last person before lunch, you're not getting out of jail. Of course, straight after lunch, blood sugar is high again, and your probability of getting parole is high. It drops quickly, though, and similarly after T. And this is a well-known phenomenon. As our blood sugar levels drop, we become more conservative. So we become less willing to take risks. So I think this happens, of course, when humans look at real data and they flag real data. So if you ask the same human to flag RFI here, if this is the first thing they do in the morning, they'll do a very careful job. If it's the last thing they do before they finish, they'll do a very poor job. But anyway, as an analogy of how tricky this is imagine you wanted to train a pixel by pixel machine learning classifier, and you wanted it to predict which pixels were grass and which pixels were not grass. So some of these are very obvious, right? These are obviously tree, etc. But what happens when you get down here? It's actually very tricky to see where's grass and where's bush or where's flower. And so that's essentially the problem, is that you have a lot of human kind of effect in here. So of course, what we did is we simulated, okay, and we will by eye or using some set of kind of simple metrics determine whether the simulations look accurate enough. So for example, here is a generative adversarial network model for sources, radio galaxies. And one of the columns is real data and one of the columns is fake data. And so it's quite interesting. I've asked many astronomers over the years to try and tell, which one's the real one and which one's the fake one. And normally I would do a poll, but I don't know how to do a poll here. So I'll just tell you that the fake data is the one on the right. And interestingly, I think it's this little point source over here that often misleads astronomers. They will think, somehow, that's the indicator. But the interesting question is, just because astronomers can't tell the difference doesn't mean there isn't some systematic bias. So, both for science, but also I think coming era for business deployments of machine learning is, how do we build diagnostic tests to search for potential systematic differences in data? And I mean, I see that Twitter just recently had this problem of being accused that their cropping algorithm was racist. And there was a very interesting kind of thread on Twitter by somebody who used to work at Twitter saying that they did try to check for race, check whether their algorithms are racist. So it's not that they just didn't think about it. It's just that they, obviously when you've got millions and millions of people trying to find a flaw in your system, it's easy. So, I think that's a very, very interesting frontier of machine learning, as to how do we check whether our data, our algorithms are good enough. So here is some examples that I would say to you. One of these columns is real, one of them is simulated. So this is now our simulated RFI data. For those of you who have worked in radio astronomy, would you like to hazard a guess, or astronomy? Well, anyone's welcome to take a guess. I don't want to put anyone on the spot, but anyone want to hazard a guess as to which one is the real data?
Yeah, they look pretty noisy to me, so I can't tell.
So the real data is the one on the left, I believe.
So close.
And the one on the right is
on the right.
The right is simulated. So you might say, well, it fooled me, or I couldn't really tell the difference, so that means it's good enough. But that may not be true, right? It might cause some serious problem. So that's an unsolved problem. But that's what we do. So what we do is we generate a lot of data, and then we train deep learning algorithms to try and detect which pixels in the frequency time domain are dominated by radio frequency interference. And so just to get into some of the details, we compared two algorithms. What we want to eventually predict is a mask. So it's a binary classification problem. At least that's the way that it's typically done, as in this pixel is clean, this pixel is severely contaminated. So we want to predict a binary mask that is the same size as the input image. And so we compared two architectures, a UNet architecture. So UNet has this characteristic downsampling. You force the algorithm down to a kind of bottleneck, and then you upsample on the other side, a bit like an autoencoder in a sense. So that was, people have done that work before. And then we developed another architecture, which we called RNet, which is essentially just a series of convolutional layers, but we allow for skipping. So this is a kind of ResNet architecture to get around the vanishing gradient problem, if you're familiar with deep learning. And in terms of execution speed, we found that RNet is significantly faster. It has a lot fewer parameters that need to get trained, and actually leads to much better performance. So what I like about this is it goes from an image to an image. So it's quite a nice thing. So if you ever need, you've got an input image and you want to output a binary mask, for example, or a mask of some sort of the same size, this is quite a nice architecture. Here's the performance. So here we plot the false positive rate against true positive. So of course, perfect performance would be, along here. And so it's quite a busy plot, so forgive me. So this is the RNet. So we've RNet 5 and RNet 6 is a 5-layer version and a 6-layer version. They give almost identical results. And you can see this is the area under the curve of the true positive, false positive rate. It's around 90%. UNet didn't do very well. It was around 60%. And then in black dots is the current code that's deployed at MeerKAT. So the current code that's deployed at MeerKAT is not a machine learning algorithm. It just looks for weird stuff going on, basically. And as a result, it has a whole bunch of free parameters, but so these dots come when you vary those parameters. And something I actually hadn't appreciated, I confess, and I think it's because maybe, I don't know, I hadn't appreciated it before we started doing this work, is I had assumed that the precision recall curves and the true positive rate, false positive rate curves were essentially the same under some essentially trivial transformation. But it turns out that that's not the case, at least in this situation. So here are the same curves for all the different models for precision recall. And you can see here where's the current algorithm that we are competing against does fairly well in terms of true positive, false positive. When it comes to precision recall, it's very poor in comparison. So this was very gratifying that we could beat the kind of current state of the art. Because of course, when we came along and we said, oh, we can do much better than the current, people were like, well, how do you know, right? Because they would just give us some data that had been flagged by using this SDP flagger. So of course, if your competitor gets to define the rules of the game, you can never beat them, right? So it took this long effort to go and develop these simulations so that we could actually have a kind of unambiguous judge. But of course, how do we know that this will work on real data, right? We've shown that it's much better on simulated data, but maybe it'll fall over with real data. And I mean, a good example in that direction is the recent work by Google on detecting diabetes from diabetic retinopathy by looking at images of the eyeball. And in the lab, they were much, much better than experts. But when it was deployed, there were significant problems, right? So you might say, well, your simulations are too simplistic. It could be something trivial, right? Most famous examples, I think back in, I don't know when it was, maybe even the 70s or 80s, when they built a neural network to detect tanks in images, and they got fantastic performance. And then somebody realized it's because all the pictures of tanks had been taken on one day when it was cloudy, and all the other images without tanks have been taken on a sunny day. And so the algorithm actually hadn't learned anything about tanks. It had just learned about the background sky. So, with these simulations, the question is, well, has the algorithm just detected something that's not real? Like, for example, there's some rounding error. For example, when we add the RFI in, it's causing some issue. So yeah, I just want to stop and check if there are any questions before I answer that question.
What was the SDP AUC that you got?
Well, it doesn't have an AUC because there's no single threshold that you can vary. At least not that we knew. But I guess what you would have to do is try and push it. So the AUC would, I guess you can do it. I guess strictly speaking, the AUC is under the precision recall curve. But anyway, the area under this graph, for example, if you just extrapolated it, would actually be probably quite close. It would be probably 0.85 on this diagram. If you were to do it over here, it would be significantly worse. I have no idea I'm not actually sure how you would push it down here into the small recall zone. So yeah, I don't know.
It's also the same with the rock curve. It'd be really hard to get it to interpolate at least up to 100%.
Yeah, exactly. Yeah, I have to say, there's one thing that I hate about these is that, of course, I can't see if everyone's bored out of their minds or paying attention. Whereas if we were in person, I would be able to see, and if people were starting to fall asleep, I would skip. So
no, we're totally enthralled. Don't worry.
Thank you. It's exactly what I want to hear. That's awesome.
Keep going.
Thanks. So yeah, so this question is how do we know that this is not crap, right? How do we know if this is real? So fortunately, we did have, courtesy of Nadeem, who is a radio astronomer, had meticulously hand flagged some data of his own. Not a huge amount, so actually relatively little compared to the amount of data that we're talking about here, which is multiple terabytes of data. Now, he's, of course, imperfect. He's a human. It's all the other problems that we were talking about. But okay, the problem was it's on a completely different telescope. It was on the 7-dish CAT array, whereas these MeerKAT simulations are for 64 antennas. So essentially, we've got this model that's been trained on simulations, very high resolution simulations, lots of data, but we have no human flag data. And then we have this other telescope, which is very different angular resolution, much coarser, lower resolution, and very little data, but that's independently human verified. So what does that sound like? Oh, that sounds like a transfer learning problem, right? So that's exactly what we did. We took the best model, this RNet 6 model. We unfroze the last two layers. So if we go back, these two last layers, we froze all the weights of the first 4 layers, unfroze the last 2 layers, and then trained our, then optimized the weights of the last 2 layers and tried out how it would do on this human labeled data. And so this is what we got. So same axes, true positive rate, precision and recall. Let's focus now on these dashed lines. So these are the results we got when we just took the model trained on the simulations and just directly applied it to the real Cat7 data. And you can see performance is terrible. Okay, the SDP flagger does much better in both precision. I mean, look at this, precision recall is just horrendous. But then when we did transfer learning, we were again able to beat the SDP flagger again by quite a long way. So, I mean, that was very gratifying. That, it's not a proof that this will work always and that there are no problems, etc. But it's a very nice, practical way of trying to go from simulations to real data. You're sort of taking the best of both worlds. Of course, assuming that your human is any good at doing their job. But in this case, I think we're fairly confident about that. So, so this is pretty good. Our next step is, instead of making a binary classification task saying this pixel is RFI, because when you say that a pixel is RFI dominated, you just throw that data away, right? And then if a pixel is not RFI dominated, you take it, even though, of course, there's probably a small amount of RFI contamination in it. So what we're currently working on is to say, okay, well, let's not just throw away data. Let's try to estimate the amount of contamination in every single pixel, because then we can just remove it, clean it. So that's our current goal. And so the question is, what's the best way to do that? And can we be clever about how we do that? And so we're looking at things like using all the different polarizations and all the different baseline. It's very technical. There's lots to explore. But so that's looking pretty promising. So now, the radio astronomy is like this iterative process where you go through these multiple stages of getting your data ready for doing science. In that sense, it's much more laborious than typical data sets in the real world. Completely different challenges, of course, because typically your telescope's built to do just one thing, whereas, of course, in the real world, you have to deploy something different, completely different every 6 months often. And so it's a very different challenge. But once you've cleaned your data, you can make images of the sky. So this is a simulated image of the sky. And now you want to actually detect stuff that's out there. And so this is, there's a whole bunch of sources there. I can't remember, but probably 1,000 sources there. So you can look really closely and try to see if you can see some points there. It's like, and you'll notice that the noise is not just a nice Gaussian random uncorrelated noise. There's like these waves, and the noise is indeed correlated. So depending on how you do this, you may see the sources pop up nicely, but you may also not. So another thing where we've applied deep learning is to actually do the source the source detection, finding these point sources. And a lot of the sources are point sources, but if you were to go to that galaxy, you wouldn't find a point, right? You'd find a giant galaxy. So they're only point sources because they're so far away, on the other side of the universe. So when relatively rarer objects are closer, and then they're very extended. And so then there's a goal of, well, how do you find these very diffuse wisps of if we did go back like this to this example, sorry for the, if we were to look at that on the other side of the universe, of course, it would just be a dot, So this diffuse gas is very problematic to detect. So we don't have a good algorithm, I would say, currently to detect very diffuse emission. So that's a bit of an open question at the moment as well. Although I think the segmentation algorithms that have been developed in the last couple of years are very obvious candidates. Just haven't had a chance to get round to it. Any questions? I'm now going to change topic. So that's a massive thrust of ours is RFI detection and excision and doing, because that is the major determinant of the quality of the images. But I'm just going to move on to some of the other interesting challenges.
Was machine learning able to clean up this image, or is that some other algorithm did that?
So no, these are both simulated images. There's different ways. So when you make an image, these images are actually, what you do is you take all the data from the telescopes and you essentially Fourier transform that data to make an image. And there's different ways that you can weight the data from different telescopes. And depending on how you do that, you would get one of these two images. So in fact, this is it's not that this is being cleaned up. It's just that there's different ways you can weight it, and it's good for different types of science. But you might want to look at this data, in which case finding those point sources is very challenging. So yeah. So it's essentially, how do you find sources when it's really right down in the noise? So maybe the way I would phrase it, an analogous problem is, how do you find the fake news that is very plausible? So that's essentially what this problem is. When your source is basically the same strength as the noise, how do you pull that out? And so, for example, let's imagine that was your job. They came, Twitter came to you and said, we want you to find all the Twitter accounts that are fake news. Like, a lot of them would be very easy, but the hardest ones would be the ones that are very marginal, right? They only slip in a lie every now and again, or it's just on the edge. And so what you'd probably, that's exactly the kind of problem that we're dealing with kind of here, except there's no malevolence involved, as far as we know. All right, so a very interesting thing about the MeerKAT array is that, it's an Internet of Things project as well, because each of the 64 dishes has of order 1,000 sensors dumping out readings every 10 seconds at least. Every 10 seconds, maybe some every few minutes. And so, that's a huge amount of data. And so, in principle, and we actually haven't had a chance to look at this, antennas have faults, they have problems. And so, a really interesting project is to go and look at trying to predict the failures of antennas. So this is very common in large factories, for example. They're very interested in that sort of thing. We did a little bit of preliminary results. We picked 100-odd sensors, divided it into pre-failure, just before an antenna failed, and then randomly sampled and looked at the covariance matrix of those sensors. This is pre-failure. This is nominal with no problems. And if you look at the difference, you see that there are some interesting correlations that would appear to signal a failure. So, one of, just like in every, I'm sure we all have this problem if we're active in data sciences, there's a list of projects that we would love to work on, and you have to prioritize. One of the problems with this project is that antenna failures are actually quite rare, and so there's not a lot of training data. So it's a kind of quasi-anomaly detection problem. Yeah, so I think one of the reasons we didn't go further with that is just trying to fit it into the right kind of framework where we've got some examples, but not many. And so how do you work with that? Another big unsolved problem is scheduling. So, you can ask, how should the 64 dishes be used in an optimal way? So, these 64 dishes can in principle look at different objects all the time. They can look at the same one, which is the default, but they can also, you could have 12 looking over there, 40 looking over there. So, in terms of achieving maximal business value, what's the best way to use those dishes? And in principle, what we want to do is actually interoperate those telescopes with telescopes around the world, and to be able to react kind of instantaneously when something exciting is happening. So at the Optical Observatory in Sutherland and also in Observatory, there's a program called the Intelligent Observatory, which is about trying to roboticize the optical telescopes and to eventually have them controlled by some sort of algorithm. So we've been, kind of tentatively looking into trying to use reinforcement learning or something like that. But it's quite hard because there's no objective, there's no obvious loss function to use for that. Anyway, so, a very nice example of this was gravitational waves. Of course, LIGO detected them, and there was this amazing situation where I think it was the first black hole neutron star merger, and that involved a collaboration of telescopes around the world and several satellites, as well as all of these observatories. So in some sense, the future of astronomy is this worldwide network that's working together in some way to optimize. And I think, that's an unsolved problem, but obviously we'll get a lot of people will be thinking about that in all sorts of contexts. I think Amazon just got permission to fly drones for delivery. So, this question of, okay, I've got a swarm of robotic things, whether it's telescopes or drones, and I want them to work together. What's the right way to do that? Very interesting problems. We have just gone through a much simpler example, but actually really interesting one that I think was a very interesting case study. They just had an open call for MeerKAT time. So this is astronomers around the world can ask for time on the MeerKAT array to observe their favorite thing. And so we had about 120 proposals, and we have about 30 reviewers, experts, reviewers, to review those proposals. And so the question is, well, we want to assign proposals to reviewers. So let's say there's Mary and John and, whoever around the world, and we need to give them proposals to review. Now, each proposal falls into one or more of the science areas. There'll be stars, and there'll be cosmology and magnetic fields and all sorts of things. And of course, we ask each reviewer to rate themselves in each of those 13 science areas. So I might say, well, I'm an 8 in cosmology, but I'm a 0 in stars. Don't send me any proposals with stars, because I'm not very good at that. So in addition, I might, as a reviewer, I might be a co-author on some other proposals. So obviously I shouldn't be sent the proposals that I'm a reviewer on. And MeerKAT team wanted that each proposal should be reviewed by 4 people to get a bit of a diversity. And there should be an expert review on every proposal. There should never be that a proposal is seen and nobody of the 4 reviewers is actually an expert. And finally, the other constraint is that each reviewer should have at least 10 proposals, but not more than 20. And so that is about just so to be able to do cross-calibration between the scores that a reviewer gives. So, I'll put that to you. How would you attack this problem? So it's really interesting. I'll ask you because you may come up with a better solution than what we came up with, in which case we'll.
I mean, not to derail the point, but this also seems like a place where you could have lots of bias due to how the reviewers in the past have treated the data and what kind of stuff that they want. And you might just enhance that kind of bias in future proposals. So maybe that's something else to look at.
Absolutely. I wasn't completely convinced that this was, especially the self-rating of reviewers. If I think, if I'm young and arrogant, well, if I'm arrogant, I might rate myself as a 9 in many areas, where someone more modest would rate themselves a 4. Although we did try to say to people, what it means to rate yourself a 3, a 5, an 8, etc. So this is, of course, not machine learning. This is an optimization problem. But what's really interesting about it, so it's a constrained optimization problem. And so initially, the route I took was, so you need to define some loss function or some figure of merit, some cost function that you want to maximize or minimize. So originally, I said that, I defined a cost function which tried to, most proposals aren't just in one science area. They might have written down 2 or 3 science areas. So proposal number 1 might say these 3 science areas are the ones that are relevant. And then when I get a group of 4 proposers, what I want to do is to make sure that they have expertise in all 3 of those areas. So I was trying to maximize the score across the combination of 4 reviewers across the 3 science areas. And the problem if you do that is that you end up with effectively a nonlinear figure of merit, nonlinear cost function. And so I used simulated annealing as a technique to try and optimize this. And it would run for 20 hours and give results that were okay but not great. And then, so in the end, what we decided was to change the cost function so that it wasn't nonlinear in that sense. So we simply said, across any of the science areas of the proposal, we just take the maximum one for each reviewer. And so we essentially moved to a less global solution. So in other words, it wasn't the combination of, we weren't looking for the best combination of 4 reviewers per proposal. We just tried to consider each reviewer independently. And the nice thing about that is it then becomes a linear problem, and then you essentially can guarantee optimal solutions, because linear programming is essentially a solved problem. And so got very, very nice solutions, but with this caveat that the cost function was missing some subtleties of the things that you might actually want to optimize for. So I thought that was a very interesting real-world example that we've just gone through of the kind of trade-offs that you sometimes have to make of, is my cost function really encoding what I care about, but I'm really struggling to actually find good solutions in that, versus here's a simpler cost function. I've got provably optimal results, but to what extent is my cost function actually encoding stuff that I really care about? So yeah, that was interesting negotiation. But it's not. You might wonder why simulated annealing was struggling. Of course, there's huge number of possible combinations, like 10 to the 70 or something combinations that So as a combinatorial problem, it's quite tricky. Anyway, yeah, and of course, one of the problems was the way you formulate the problem was really critical. So the way you decide, you can set this problem up in 2 or 3 different ways, and depending on which way you get, you can make which way you go. You can make rapid progress, or you can struggle. But one of the hardest things about this is it's integer problem. The reviewers have an ID, and you say, okay, this proposal number 17 must go to reviewer number 12. You can't say it must go to reviewer 12.6.632. And of course, integer problems are much, much harder than continuous problems because you can't use derivatives. So anyway, so back to the science and back to interesting, cool, exciting science. I think one of the most amazing opportunities, especially for South African science, is anomaly detection. So what I mean by anomaly detection is obviously finding weird stuff in the data. So this is the opportunity to discover things that have, to discover a Nobel Prize. So in here, there's a Nobel Prize. Probably wouldn't take you too long to find it. I'm sure you've all discovered it already. It's there. The Nobel Prize is hanging out there. What made that relatively easy, of course, is the fact that you know what a Nobel Prize medal looks like. If, on the other hand, I said there's something weird in this image, find it, and it was because one of the leaves is a perfect square, for example, it would have been much harder to find. Or if there were 5 pixels that were blue, it would have been much harder to find. So that is the challenge with anomaly detection. So, what we're really looking for, we really want to try and find these kind of objects in the data, new objects that have never before been seen. But of course, we don't know what we're looking for. And with an exabyte or even petabytes of data, humans can't look at that. So the question is, okay, well, how do you approach that problem? And in a way, it's a little bit similar to the problem of cybersecurity or cyber hacks, right? Is that you're in the cybersecurity context, you have an adversary who's adapting and is trying new things, and so you very may have an attack that you've never seen before. In nature, presumably, there's no one there trying to create weird stuff just to screw with us, but it's just the sheer volume out there in the universe that is causing this novelty that we don't know how to deal with. And so just to illustrate the problem is, the real problem comes about choosing the features that we want to plot the data with. Once you've chosen these features, it's very easy to spot outliers. There are many algorithms that will do that quite efficiently. Isolation forest, for example, which is built on random forest, or local outlier factor, those are two, but there's a million algorithms. The problem is, what happens if for those particular choice of features, X1 and X2, your anomaly is lying slap bang in the middle of a normal cluster? So really, at the heart of the anomaly detection problem for me is, how do we pick features so that the anomalies will be visible? And so let's use this like shark, seagull as an example. If we were to pick as X1 and X2 the number of legs as one of our features, this thing isn't going to look anomalous, right? If we plotted X1 is the number of legs and X2 is the number of eyes, then this thing would just be slap bang normal, right? If, on the other hand, we switched from the number of legs to the number of teeth, we would suddenly see, oh wow, this thing really is weird, right? It's a bird that's got a huge number of teeth. That doesn't compute. So in a sense, that's, I think, is the real challenge in anomaly detection. How do we learn features that make the object stick out? And of course, this is, in its most extreme form, is impossible. There's the no free lunch theorems, which guarantee that basically there's no such thing as the best anomaly detection algorithm. There's no anomaly detection algorithm that will work for all anomalies. And one way to think of that is, imagine if I ask you to design a trap to catch a new type of animal. You might ask me some questions. You might say, well, do you know roughly how big it is? And I say, no. I have no information about the size. Okay, so it could be the size of a single cell, or it could be the size of a planet. Immediately it's you wouldn't, there's no trap that you can build that will work across any size, yet alone what is it made of, etc., etc. So it's basically an impossible problem, except that we know that, of course, in astronomy at least, they have to obey the laws of physics, and it's got to be bright enough, so that to be bright enough, it's got to be fairly big, and if it's big, it obeys the laws of the kind of standard laws of physics. So we're not trying to build a completely general anomaly detection algorithm. We're trying to build a somewhat more restricted algorithm, and it's not clear if there is an optimal algorithm in that context. So I think that's very interesting. Here's another way in which anomaly detection in science is a bit more challenging. If someone gave you this data and said, where's the anomaly, you would say, well, it's obviously that. But in science, unlike NLP, natural language processing, or other data, in science, we typically have error bars. We have an error on our measurements. So, for example, if I said to you, oh, this is now the data, where's the anomaly? Well, this appears anomalous, but it would be very consistent, very easy for this data to actually, the true value of this data to lie in the middle here. And in fact, this object, if it really had tiny error bars, might actually be the anomalous object. So, here's a question. How do you do anomaly detection, or even how do you do classification if your data has error bars on it? It's quite an interesting problem, and all of our data has error bars on it. It's actually one of the things that, of course, characterizes science, is that we can put error bars on our data. And I suspect that this is another element that will come more and more into mainstream machine learning. I mean, obviously, it's already starting with things like self-driving cars, with medicine. When an algorithm says, I think this person has cancer, I think that's a tumor, you want to have an error bar on that, how confident is the algorithm. And I think more and more that will come into mainstream machine learning, especially for autonomous systems that are deployed without much human oversight. So anyway, I mean, I can tell you what the answer is. We have developed a Bayesian anomaly detection algorithm that takes the error bars into account. It's horrendously slow in comparison to the standard algorithms, but it does give you unbiased results. Because of course, one of the problems with standard machine learning algorithms for classification, for example, you might say, oh, a random forest, logistic regression, or even standard neural networks, it tells me that this thing is a dog with 80% probability. But there's no sense in which that is an actual probability. It's just a number between 0 and 1, right? And if you add up all the predictions over all your classes, it will add to 1, but there's no sense in which, 80% of the things that you give a score of 0.8 to are actually dogs. So they're not good probabilities, whereas there are statistical methods like the one that we developed that will give you calibrated probabilities. So I think that will be another growth area. So it's like, I think I kind of see machine learning and data science and traditional statistics, at some point they're going to have to kind of merge and form some there must be a field of rigorous machine learning. And I guess causality will have to come in there at some point as an important component of that. So that is a kind of brief tour of some of the things that we've been working on. I've already gone over an hour. I apologize. We did have that thing. Again, if I could see your faces, I would be able to judge whether this was a disaster or not. I'll end maybe with just a little speculation. As part of this, I went back over many years of slides, and I found a 2011 talk called Rise of the Machines that I gave in Paris. And in that, I was really interested about, will it ever be possible for AI to do real research, to do great research, to discover something truly profound about the universe? And I had a couple of people just walk out of that lecture. It was at the university, one of the universities in Paris, and people were very upset because I was basically saying that a computer could do what researchers do, and of course no one wants to hear that. But I think my opinion hasn't changed. I think it won't be very long before AI really can do interesting research. But I'm happy to debate that. And maybe I'll stop there and invite questions or comments or thoughts.